Welcome back to the first ARC seminar of the term. Today we'll have Isabella Pretto talking about the Hilbert-Huang transform. Yeah, feel free to get started.
Thank you. Hi, everyone. For those who don't know me, I think I know everyone in here. But anyway, introductions are always nice. I am Isabella. Why am I saying Isabella pointed to a black hole? Well, that's a good question. I am a second-year grad student working with Saltopolsky, so I'm part of the SXS group. I graduated from Columbia in 2022, and the reason why there is an AGN as part of my presentation is because that was my first research experience. So I started astrophysics I started doing research in astronomy in high energy astrophysics. I worked with Rashmi Mukherjee, and the reason why I'm telling you this is because that was a very special experience to me, because when I was a kid, not that young, but still a kid, something that I used to think about was like, okay, so astronomers look at the sky and they collect, and then they look at the sky and they somehow come up with all of these theories and explanations as to what's happening out there. Like how does that happen? Like what is that connection? And that's and in school I learned about the scientific method and what data analysis does and what data analysis is. And that experience that I had in undergrad with high energy astrophysics and doing AGNs and gamma reverse was really my first experience doing data analysis and seeing the day-to-day. And that drew my attention to analysis and data analysis and what that means, and the importance of having really good tools, because if you don't have really good tools, then the data that you collect is just, it's garbage, it's meaningless. Okay, so what's up? What's the problem with our current methods and the way we normally do data analysis? So traditionally, our data analysis tools are for stationary or linear data. And what does stationary mean? It means that the statistical properties like the mean and the variance don't change with time. And linear means that, for example, you can, well, I guess I don't have to explain well. Linear data is exactly, thank you. But the question is, does that actually describe the real world? Because, well, weird science detections are like, they usually appear as bursts or things like that, things that are non-stationary. You need some so you do have some time dependence there. So it gets tricky when you use transforms like the Fourier transform, which does depend on which does assume stationarity and linearity to analyze your data, right? So we do have other tools like the wavelet transform, which is I think is what people in LIGO use, but still, if I'm not wrong, you do the wavelet transform works for nonlinear signals, but you still have the assumption of stationarity. So yeah, and one of the problems with that is that all of these really nice statistical tools which do have a really nice mathematical formulation, have an a priori basis. So for example, what that means, for example, when you use Fourier transform, is that you are using trigonometric functions and a linear combination of these functions to express your data, and then you do a convolution computation. And the problem with that is that that also leads to an issue with the resolution of frequency and time. So as we all know, the more well-defined our signal is in the time domain, the less well-defined it is in the frequency domain. So what that means is that we need to start looking for something else. So an a posteriori basis or an adaptive basis, where we don't impose any mathematical other mathematical functions or rules, but instead we let the data speak for themselves. So we don't, as I said, we don't apply functions, we just decompose the data and look at the data to find this basis. And another reason why that is interesting is because at the end of the day, the functions that you use as a basis are sort of arbitrary. So there is nothing in the real world that tells you that necessarily you have to express that a process can be expressed as a linear combination of trigonometric functions, for example. So that allows you to have a different way of understanding physical processes. And that's the context in which the Hilbert-Huang transform was developed. So it was designed for, not linear. It also works for linear, but it was designed for not linear, non-stationary data. So the Hilbert-Huang transform is a combination of the empirical mode decomposition, which I'm gonna explain later, and the Hilbert transform, which I will also explain later. So essentially the empirical mode decomposition, just as the summary of what it is, it allows you to decompose your signal into intrinsic mode functions, which are your bases, and on which you can apply a Hilbert transform to get the instantaneous frequency and the instantaneous amplitude, which is essentially what we are looking for, and what will help us to deal with the problem of non-stationary signals and non-linearities. So the idea is we start with our data set, apply the empirical mode decomposition, get the IMFs, and then we apply the Hilbert transform. And in this way, we can derive more physically meaningful instantaneous frequencies and amplitudes. Okay, so let's begin with the Hilbert spectral analysis. So as I just said, one of the reasons why we use the Hilbert spectral analysis is because it has a definition of instantaneous frequency and instantaneous amplitude. So if we have a time series xt, we can just define the Hilbert transform as yt, which is the principal value of the Cauchy principal value of this integral, which is essentially like you were using the separation from your t as a sort of weight. And using that, you define a complex signal whose imaginary part is the Hilbert transform of the real part. And that allows you to define an amplitude and a phase that depends only on time. And that gives you a definition for the instantaneous frequency. So instead of thinking about frequency as the inverse of period, we think about frequency as the time derivative of the phase function. And if our capital H is the square root of the amplitude, because the amplitude depends on time and the frequency also depends on time, we can define the energy associated with the given frequency as the integral over the time domain of their signal of the squared amplitude, which should depend again on the frequency and on time. Okay, so that sounds really cool, almost like magic, but of course there are limitations because life can be perfect, right? So what you are seeing here is essentially a perfect IMF. So xt is your signal. This exponential gives you the time-dependent amplitude, and the term inside sine should be your phase function. So if you take the derivative of that, you get instantaneous frequency. So on the upper plot, you have the signal. You have two signals. The one in green is like this function xt, but riding on a mean of 2. So we were adding just 2. We were adding a constant of 2 to that signal. And the blue line gives you the same signal, but without that constant. And the lower plot, you have the instantaneous frequency that you get using the Hilbert transform. So actually, like for the black curve gives you the real instantaneous frequency. The blue curve, the Hilbert transformed instantaneous frequency that you get when you have a zero mean. And the green curve, the Hilbert transformed instantaneous frequency that you get when your wave is riding on a line of constant amplitude too. And a few things that you can observe is that when you have your wave, when there's a trend, then first your instantaneous frequency is qualitatively different from both the real frequency and the frequency when it is the Hilbert transform frequency when it is not writing on anything. And the second thing that you're going to observe is that you also have negative frequencies that are just not right. Now, back to the blue curve, you do see that there are some irregularities towards the end, and these things are pointing to some limitations in the Hilbert transform that we're going to deal with later. So what Huang noticed was that a necessary but not sufficient, as you saw, condition for the Hilbert transform to work and give you something that can give you an instantaneous frequency that is physically meaningful is that you have a purely oscillatory function, and you have a zero reference level. And the zero reference level, this condition for the zero reference level is very clear back here when we saw that the Hilbert transform instantaneous frequency of a wave that is riding on a non-zero reference level is very different from the one that is riding on a zero reference level. And then the question became, how do you decompose an arbitrary function in terms of functions that do have a meaningful Hilbert transform so that we can apply all of this technology to derive instantaneous frequencies that are physically meaningful. And that's what led to the development of the empirical mode decomposition, which is the second part of the Hilbert-Huang transform. So the Hilbert transform is what we just talked about. So giving you instantaneous amplitude and instantaneous frequencies. And the Huang part comes with the empirical mode decomposition, which is essentially, again, slicing your data into bases that can give you a physically meaningful instantaneous frequency. Okay. So the assumption is that your data is a superposition of oscillatory modes with very different frequencies, and that's going to become clearer later on when we look at what the IMF or what the EMD, the empirical mode decomposition, actually does to your data, and what the IMFs look like. So, so what's the definition of an IMF? So essentially the basis that you were using to represent your data. First, you need that the number of extreme and zero crossings are either equal or they differ by 1, and that so what we're gonna do is, let me see if I have another plot here. So here's an example of what your data looks like. So if you look, for example, at the first plot, you do have like maximum, minimum. And then one of the things that we're going to do is we're going to define an upper envelope connecting all the maxima and a lower envelope connecting all the minima, and that's going to give you a mean. And the condition for your signal to be considered an IMF is that that mean is 0. And then, yeah. So once we do that, we find our first IMF. We're going to continue decomposing the function through a sifting process, which I'm going to explain here. So on the first plot, you have your data. So as I was explaining, we start by identifying all the local maxima and minima. So we have the local maxima in diamonds and the local minima in circles. Then we're going to connect using a cubic spline the local maxima, forming this upper envelope, and the local minima forming this lower envelope. And sorry. The dashed line is giving you the mean of these two envelopes, and you're going to get your first proto mode by subtracting that mean from the signal. So that gives you D. And then you're going to ask, does this signal satisfy the conditions of an IMF? And usually the answer is no, it doesn't. So we're going to continue doing that, namely, identify your local extrema, get your upper envelope, your lower envelope, compute the mean, subtract from the initial data, and get another proto mode and check if it satisfies. And if it does, you're going to subtract that proto mode from the original signal, getting something that looks like this, which is your residual. So as I just said, you're going to continue iterating until you find something that satisfies the definition of an IMF. And the reason why we do that is because we want to eliminate background waves. So we want to eliminate those trends that appear, and to make the wave profiles more symmetric. the way you make wave profiles more symmetric is by imposing the condition on the mean, and the mean has to be approximately 0. And the way to think about that is that, well, the mean would be approximately 0 if there isn't much of a difference between this point and this point, because I'm using a cubic spline here, so they should be more or less symmetric, so that the upper and the lower envelope will more or less cancel.
Sorry, can you say again, like, so if we go back a few slides, how does the formal criterion for ending this algorithm correspond to that?
That's what I'm going to talk about.
Okay.
I think that's actually the very next thing. Is it? Oh yeah, after this. So as I said, we're gonna C1 is your first item. So you subtract that from your data, get your first residual. Then we're gonna do the same thing on the first residual. Find the IMF from that. That's gonna give you another residual. We're gonna continue iterating until you don't have any meaningful oscillatory signal. So until your residue becomes a function that is either monotonic or has only one extremum. And that's how you're going to represent your data. So as a combination of those phases, Cj, that should give you physically meaningful instantaneous frequencies as per the definition of an IMF, plus this residue that doesn't give you any information about frequencies at all. And what we are seeing here is an example from a project that I worked on. So this is data from one of our simulations. On the first plot here, you have the area mass of a black hole from a binary. And early on, you can see this irregularities. That's what we call that's the effect of junk radiation, which is what happens when we evolve binary black holes because the initial data is not perfect. And the second plot, we have the first IMF, the third, the second, that's sort of confusing. And it keeps going until the fourth IMF because the signal only had 4 IMFs. And then you see the residue. So essentially, if you added these things, you would be able to reconstruct the signal. And something that you can observe is that the IMFs, they have different frequency ranges. So the first IMF is supposed to have the highest frequencies of the signal. The second highest, and it keeps decreasing until you have only the very low frequency range on the fourth IMF. Yeah.
Depending on how you interpolate between these global maxima and minima, your eventual residue may not be unique.
Yeah.
Is that a problem or?
Yeah, we're gonna get to that. Yeah. So I think that is related to your question, the stopping criterion. So yeah, so when do you stop sifting? Because a few things that you have to keep in mind is if you sift way too much, you're gonna lose the physical meaning of your data. And if you don't sift enough, then why are you doing this empirical decomposition to begin with? So there are some things that we can keep in mind. So the first thing, this is what people usually do. It's a Cauchy type of convergence test. So you are essentially, there are 2 types. They're very similar. You're essentially comparing the mean, which is never actually 0, but very close to 0, to the amplitude of your IMF. So the difference between these two is that in the first case, you are comparing the mean. So let me go back to one of the slides. In the first case, what you are doing is you are comparing this amplitude from a given IMF with the mean of that same IMF. And in the second test, you are comparing the mean of this IMF with the amplitude of the next IMF, which is that IMF, which is the data minus that IMF, if that makes sense. Yeah, so the problem with this is first you have to specify how small is small enough, because that's never going to be actually 0. And the second thing is that, okay, so that could help you satisfy the definition, the second part of the definition of an IMF, which is that the mean should be approximately 0, but that doesn't tell you anything about whether the number of extreme and the number of zero crossings are equal or differ by 1, which is the first part of the definition. So we can use another type of criterion, which is the acid stoppage. So essentially, you stop sifting when the number of zero crosses and extrema are equal or differ by most 1. So that's good for our definition, satisfies our definition. And when it stays the same for as consecutive times. And there is a lot of research that was done to find empirically what's the best S value. And they found that it's between 3 and 8 because, as I said, you don't want to undersift, you don't want to oversift. So there should be some balance there. I think 5 is the optimal value that they find. Okay, so some of the properties of the empirical decomposition, I think that goes straight to your question. So usually, and I emphasize this usually and empirically, because this is an empirical method, your IMFs will satisfy requirements of convergence, completeness, and orthogonality and uniqueness. And because of that, you can express the data as this combination. And if you notice, I'm not including here the residual, and the reason why I'm doing that is because the residual doesn't give you any information about the frequency. So you might as well just represent your data as a combination of these IMFs without the residual. And you can compare that to a Fourier representation of the same data. And what that is showing you is that you can think about the Hilbert-Huang transform as the generalized Fourier representation, Fourier transform, generalized in the sense that you are allowed to define an amplitude and a frequency that depend on time rather than keeping them as constant. So a generalized Fourier transform and generalized because frequency and amplitudes are allowed to depend on time, which serves our main goal of being able to represent the data set that is nonlinear and non-stationary. And the other thing that we gain by doing this is, yeah.
Isn't this also an a priori assumption of using sinusoidal waves as basis for all the time series here in?
Yeah.
So,
but I would say that the main difference is because here you are allowed, you can model, for example, intra-array frequency modulations because you allow the main difference here is that your frequency and your phase are allowed to depend on time. So in that way, it is different from the Fourier transform. But yes, it was already sort of implicit because you do model that as a sinusoid. Yeah, and the other thing that you gain by doing that and using an adaptive basis is that again, you are not subject to the uncertainty principles and to the uncertainty principle that impose a limitation on how well you can resolve frequencies. Yeah, so something that we also assume in doing this transformation is that the variations that you have in the phase function are a lot greater than the variations that you have in the amplitude, that for an IMF. And the reason why that's the case is because by definition, an IMF has a zero mean, and you can only have a zero mean if your amplitude is not varying that much. And the way you express that mathematically is by requiring that the Hilbert transform of the product of the amplitude and the cosine of your phase function is equal to the amplitude times the Hilbert transform of the phase function. But the problem is that we have something called the Petrosian theorem, which tells you that you can only express that the Hilbert transform of a product of two functions can be expressed as one function times the Hilbert transform of the other, only if we have spectra of those two functions do not overlap, so they must be completely disjoint. And if the frequency range of the spectrum of one of the functions is a lot greater than the frequency range of the spectrum of the other. And again, a way to think about this intuitively is by thinking that f of t should be more or less constant, is more or less constant when you compare that to the variations of ht. But the problem is that that is not what usually happens, because in real data, you should not expect that the frequencies from your carrier wave and the frequencies from your envelope do not overlap, because they do overlap. And how to deal with that? So how to construct an IMF such that the phase function will be the one that will be giving you information about the frequency only. So Hilbert came, so Huang came up with this normalized transform, which allows you to separate your IMF into two components, so an amplitude modulation and a frequency modulation component. And the reason why you want to do that is because, again, you want the frequency component to have all the information that you were looking for to represent the frequencies from your data. And after you do that, you can apply the Hilbert transform to the frequency modulation part only. So you were escaping the Vidrosian theorem that imposed that limitation on our decomposition. So the way you do that is first we get the absolute value of the IMF, then we identify all the maxima, then we define an envelope through all the maxima. So let's see if I have there. Yeah, so here what you would do is essentially you would flip the y-axis so that you would get only the absolute value of your IMF. Then you would do something similar, like you would connect all the maxima, creating an envelope, which we here call E1. Where is it? Yeah, then we would define that envelope, and then we would normalize by dividing the data set by that envelope that we get. But because this is real life, sometimes, it's not going to work well, and your function f will not look like a cosine or even have the same bounds as a cosine. So you're going to continue doing that until your function is between 0 and is between -1 and 1. And in doing so, you can define your FM, and your amplitude modulation components. So here you say that F is your frequency modulation components. Did you raise your hand or something?
No, I scratched your hair, sorry.
Oh, sorry. And then you divide your data set by your frequency modulation to get the amplitude modulation part. So this is what we call the normalized Hilbert transform, which is this normalization scheme plus the Hilbert transform that is applied to the frequency modulation part only. So here we have the same function that we were using before, and on the upper plot, we have the instantaneous frequency as a function of time. So the blue line gives you the real instantaneous frequency, and the green line, the instantaneous frequency after we apply the normalization scheme and apply the Hilbert transform to the FM part only. So you can see that this looks a lot better than the function that I showed you, than the plots I showed you in the beginning. So we don't have that instability anymore, so that's good. That's an improvement. But something else that you're going to notice is that the errors are quite large. Don't worry about the magenta line. I'm going to come back to that later. And how do you fix that? Because essentially I've been trying to sell you the idea that the Hilbert-Huang transform is an amazing thing that allows you to find instantaneous frequencies. But yeah, it does, but the errors are also somewhat significant.
So what does error mean in this case?
That's the difference between the real frequency and the one from the Hilbert transform. So the blue, can you see the blue line? Because
right, so the real frequency is like the stuff in the sinusoid divided by t, or what is
that's the derivative of the phase function. So the derivative with respect to time of whatever is inside sine.
Right.
That's the real frequency.
So this is more error than is expected from like the hypothesis that the phase function is fast varying.
This is more error than you would like to have. So what this is essentially telling you is that even if you have the first IMF, which we constructed so that the Hilbert transform would give you something that is physically meaningful, even if you're in the best case scenario, you would still have errors that are large. And what we want to do is fix that. And how do you do that? So we have something called the direct quadrature method. And the idea is that maybe you can just get rid of the whole Hilbert thing and just take advantage of the good properties of the IMF. And how do we do that? Well, we have our data, it's going to be decomposed into IMFs. And now that we have this normalization scheme that allows us to decompose an IMF into AM and frequency modulation parts, we can just use the R cosine of the phase function, which should give you the phase, right? And that's what we, yes. And that's what the magenta line represents. So the frequency that you get when you use the certainty frequency that you get when you use the direct quadrature measuring stat of the Hilbert transform directly. So as you can see, the errors are a lot smaller, and the overlap between the blue line, which is the true instantaneous frequency, and the magenta line, which is the one from that quadrature method, overlap really, really well. And another thing is that the errors follow a very specific pattern. And so you can also fix for that and get really good results. Okay, so another thing that you may want to ask is, how do we know whether a decomposition is reliable, and how can we assess how good the decomposition is? Or is that, I think someone asked about this, was it related to your question about the stoppage criterion?
Sure.
Okay. Yeah, so how sensitive are our results to the stopping criterion? Because I just told you that we have something called the S number, and if you continue sifting, you're gonna get a different composition. So how do we know that we stopped at the right place? So the idea is we check for some sort of convergence of a given IMF by using different values of stopping criterion. And what that means is you start with, say, you allow your S to vary from, in this case, 4 to 13. And with each value, you decompose your data using the different values of S. And then you get your first IMF. For the first IMF, we're going to collect all of the first IMFs. We're going to get the mean of that, and also the spread. And you're going to compare that. You're going to pick the one that has the smallest spread and to find that as your first, as your real first IMF. And you're going to do that same procedure with every other IMF, which is essentially what you were seeing here. So here on the first plot, you have your real data. And then the second plot, your first IMF. So the blue line gives you the mean, and the red line the spread with one standard deviation. And what you were seeing is that the first, the second, the third, and maybe a bit of the fourth IMFs have a very small spread, so you can trust them really well. But the last two are not that good. Yeah. So
What do you mean trust? What do you mean by trust them?
So your trust on this method is related to how well your sifting criterion is. So what this is telling you is that your first IMF, your second, and your third are mostly independent of your sifting of your S number within a given range, which is how you can tell whether that's a reliable decomposition or not. It should be mostly independent of your S number within a given range.
So how does the S number affect the first modes? Because this is the stopping criterion, right?
It should affect every mode, but is affecting the first modes less than it is affecting the other modes.
So the stopping criterion is basically saying like when I should stop looking for basis functions, right?
This the stoppage criterion is telling you when your IMF is complete. When you have one IMF. So you have your data, you're gonna do sifting until it satisfies the conditions for the definition of an IMF.
Okay, oh, it's okay.
And the sifting, the stopping criterion is telling you quantitatively when it satisfies those conditions.
Okay, I see, yeah,
Yeah, does that make sense?
I think so, yeah. There are two loops going on. Yeah, so S is controlling when you find a basis function, and then
Yeah.
there's another criterion for like, I'm done with finding.
With finding
Yeah,
basis,
I see.
yes.
Okay, yeah.
Exactly. Okay, so another question that you may think about is, okay, so the data that we usually deal with is noisy. So how do you know that an IMF is representing real data instead of noise? And to do that, we have to look at the spectral properties of noise in the EMD. So essentially, you're asking the question, what does an IMF from noise look like? And we had Flandrin and Gonsalves who studied Gaussian noise, and Hilbert-Huang who studied white noise, and they both found properties that are common across the different types of noise. So first, the spectra of all IMAPs except the first one will collapse to a single shape when you have on the x-axis the log of the frequency with an amplitude that is allowed to vary. And another good thing that they found was that the central frequencies of IMFs, of neighboring IMFs, so first and second and third, they are always halved. So using these properties and also the central limit theorem, they were able to derive the expected energy distribution of IMFs of noise series, and also find a form for the spread or the standard deviation of your distribution. And what that does too is it allows you to establish a statistical significance test that you can use to tell whether your data comes from noise or actually real data. So here we have an example of what that looks like in practice. So the bold, is that bolded? Like the really dark without dots line in the middle. So that's the expected energy distribution. So on the y-axis you have the log of the energy, and on the y-axis, and then on the x-axis the period, and black, the center line is expected energy distribution. The upper dashed line is gives you the 99th percentile, which means that you would expect 99% of your data to be below that. And the lower one gives you the first percentile, so you would only expect 1% of noisy IMFs to be in that part of your parameter space. And the targets are giving you the energy from those IMAPs that we saw from that data and from those other plots I showed before. What else? Yeah, so another way that you can test for whether you are looking at real data or noise is by using a Monte Carlo test. So we start with a noise series that has the same length, the same size as your real data. You generate lots and lots of samples, and then you decompose all of those samples into IMAPs. And say that you have a quantity that you are interested in, so you're gonna find a statistical distribution of that quantity over the different IMAPs, and then you're going to find that saying you're going to look for some sort of statistical description of that, like the mean and the spread. And then you're gonna calculate that same quantity on the IMF of your real data, and you're gonna see where the quantity lies on the distribution from that those noisy IMFs. Does that make sense? Yeah. Yeah. Okay. I guess that's all that I had to say.
Is there a generalization to, like, is it possible, so this can identify basically like uncorrelated white noise.
Yeah.
But if you have some kind of correlated noise, is there some kind of generalization of this?
I'm not sure. I know that that applies to white noise and Gaussian noise.
Mhm.
I don't know if you about other types of noise. So main takeaway, if anything, remember that Hilbert-Huang transform allows you to analyze nonlinear, non-stationary data that you can find. You can define instantaneous frequencies and instantaneous amplitudes that could be physically meaningful. And that's an alternative to the spectral methods that we have. So something to add to your toolkit as a physicist. Yeah.
Do you have an example of?
No, go ahead.
Questions?
Yeah, Q&A.
Yeah, just as wondering if you have an example. of this on.
Yeah. So here I used that for my research. This is the empirical decomposition. I didn't actually use the frequency because it just wasn't applicable. It wasn't really helpful in this problem. But here I have the area mass evolution of a black hole, and my goal here was to find a way of telling where junk radiation ends in our simulations. And I used the empirical decomposition for that because essentially what this is doing is the first IMF is giving you most information that you need about junk radiation, which are this fluctuations that you see early on. And the zero mean is very helpful because then you can define a criteria that would tell you when junk radiation ends based on the amplitude of this signal, because the mean is already zero.
What if your time series is, say, evolving, or the amplitude is increasing with some perturbations in it? Your mean of two envelopes, the global maximum and minimum, will never be zero, right?
Yeah, so that's another advantage of the Hilbert-Huang transform. So it does the trending that you want. So when you are computing an IMF, you are only looking at the difference between the mean and the signal. So you are removing the trend, and ideally where is it? The residual will remove that trend. So here you can see the purple plot is a residue, which remove that. So that it's not, your signal is not writing on anything, or if it is, then it doesn't matter.
Okay, so there have been like some like motivating features for why we want to use it, like, to tell a signal apart from noise and this other application. But so part of the talk was about basically like, oh, how do we define like a meaningful frequency, time dependent frequency, right? What is a context in which I would want this? I mean, I guess in gravitational waves maybe it makes sense, but why would we, do you have examples for when we would need this and some other method might not do?
Junk radiation is an example, or whenever you have a signal that is oscillating very fast, and it doesn't make sense for you to define a frequency over the entire domain.
Okay, so yeah, okay. So in the junk radiation application, you do. What is the reason that you want to know the frequency as a function of time?
You don't actually need to know the frequency, but so your data looks a lot like a bunch of random oscillations. So the way you as a human can tell that that's junction radiation is because you have a bunch of highly oscillating signal. And how do you remove that? How do you tell a computer where those oscillations stop? And that's, for example, when you can use this algorithm. And I guess like essentially whenever you have in your data a burst with a very different frequency, just because physics, then it is good to have something that can tell you what's instantaneous frequency if it's a short burst.
Yeah, that's true. Okay. Yeah, I don't know how they do that though.
So I've used the stationary phase approximation in the past. Is this like the inverse, like data to model instead of model to data for that?
Can you explain?
Yeah. I mean, the stationary phase approximation is just like say I have a function that is a of t sine of some g of t, and then g of t is varies but much if the exact condition, but basically that g of t varies on a much longer time scale than the magnitude of g of t, basically.
Okay.
So because that is to say that there's some fast oscillating part and some slowly evolving frequency, then you can that's how I have in applications extracted a sense of frequency as a function of time. I guess, is this like the inverse where I have data and I'm trying to, because a lot of the equations look reasonably simple.
We can go back a few, and I think there's an equation where you show the hypothesis for factoring some amplitude function out of a Hilbert,
when we removed.
which is I think
Yeah.
the consequence of that.
It seems
Right.
similar, so.
That's exactly it.
Okay.
But here our assumption is that the amplitude of an IMF varies very, very slowly. Yeah. Does anyone have any other questions?
Okay, if not, we can thank our speaker again. Thank
Thank
you
you.
very much. So regarding scheduling, I've been told that this time is not convenient for some people. It's also kind of annoying to be right after GR. So
My brain is like dead at this
on
point.
weeks where there isn't a Monday holiday, I will try and make it on Monday at 4, but I'll send an email about that. And then on the other days where there is a Monday holiday, it's just I can't avoid that, unfortunately. Cool. Please enjoy the snacks, especially you.